Welcome and thank you for joining. In this lesson, we'll explore solving some more complicated systems of equations. Recall that so far we have looked at three different methods of solving systems of equations: graphing and two algebraic methods. We call them substitution and elimination. So when we draw the graph of a line, we say that any point with coordinates x and y on the graph of a line would satisfy the equation or is a solution to the equation. So the solutions to the equation of a line y equals mx plus b are the coordinates of any point on the line, because those coordinates will turn the equation true. Now, when we have two equations, we're going to say that, for example, in the blue line, all these points will be solutions to the blue line, and all these points, and if you want to count them, as we have discussed in class, there is infinite number of points here, and we're going to say that all these points on the pink line will satisfy the equation of the pink line. Now, there is only one point that satisfies both of the equations of the two lines, and this is what we call the point of intersection, or the solution of the system of equations. So as you can see here in the first two examples, these two lines have one point of intersection. So if you were to analyze the equations, like the slopes and the y-intercepts of each equation, then you would say that the slopes are different. Obviously, you can see that the steepnesses are different. So that means that the slopes are different. And in the meantime, if you look at the y-intercept is also different. So that will give the system one solution. And the second case is when the slopes are different and the y-intercept may be the same as well. And in this case, we're going to say that the y-intercept is actually the point of intersection. So we're going to say that the condition for two lines to have one point of intersection is that their slopes are different. So the y-intercepts may be different or may be the same. They still can have one point of intersection. Now, the second case that we looked at is when the two lines will have the same steepness, so the same slope, but different y-intercepts. So this will form two parallel lines, which means that they will never meet each other, so they will never have a common point of intersection. So if we have these two equations in a system, then we will say that there will be no common point of intersection, which means no solutions to the system of equations. And we call these two lines parallel. And that happens again when slopes are different, and very importantly, the y-intercepts are different. So because that what the y-intercepts being different creates this gap between the two lines and makes them parallel to each other. Now, the last case is when two lines may have exact same steepness, so they are parallel, but they also happen to have the same y-intercept. So if they have the same y-intercept, then the rest of the points will be the same because they're parallel. So in this case, we're going to say that any point on the line, on the blue line, the coordinates of any point on the blue line will be solutions to any will be points on the pink line. So the solutions to the blue line will be solutions to the pink line, which means that the two lines will intersect at an infinite number of points, so there will be an infinite number of solutions. In this case, we call these two lines coincident, and the condition is that both the slope and the y-intercept will be the same. Now, when you solve these particular systems of equations algebraically, we end up, when we have one solution, we end up with, for example, if you're solving for x, with an equation of the form a number times x equals some number, and this number here, very importantly, has to be different than 0, whereas this number here can be any real number, including 0. So, and that's how we know that we are getting one solution to the equation. So for example, we may end up with things such as negative 2x equals 5 and x equals 5 over negative 2. And then you can find the y-coordinate, the same way for all systems of equations by substituting it into the other. Now, if this number happens to be a 0, that's okay too, because you would be in a situation when you have 2x equals 0, x equals 0 over 2. So that means that the x-coordinate at the point of intersection will be 0, which means that most likely this is going to be on the y-axis. The point of intersection will be the y-intercept. So that is still one solution. Now, when an equation has no solutions, then we end up with 0x equals a number. Again, this number on the other side can be, on the right side, can be any real number. And as you can see in here, coefficient x will be 0, which means that x has to be any number divided by 0. And we know that we cannot have a 0 in a denominator because division by 0 makes no sense, which means that such x doesn't exist, which means a solution or a point of intersection between the two lines doesn't exist. Now, when a system of equations has an infinite number of solutions, algebraically, we're going to end up with an equation that looks like this: 0x equals 0. So as you can see in here, no matter what you substitute for x, this equation will hold true for any real number. So the reason why is because when you multiply any number by 0, then you get 0. So we're going to say that we are getting an infinite number of solutions. So an infinite number values of x can satisfy this equation because any real number can satisfy this equation. Now, this is a very important concept we need to keep in mind when we solve any system of equations. And I thought that it's a good idea to kind of refresh